Welcome to this presentation on a circular polarization MIMO antenna using sequentially rotated feeding network for WLAN applications. This research introduces a wideband circularly polarized MIMO antenna operating at 5.5 gigahertz, utilizing two identical 2x2 subarrays and aperture-coupled elements to enhance bandwidth. Modern WLANs demand high spectral efficiency, frequently constrained by the narrow bandwidths of traditional microstrip antennas. While MIMO technology addresses capacity, placing antenna elements in close proximity introduces severe mutual coupling, degrading overall system performance. Furthermore, existing solutions often suffer from low gain, restricted bandwidth, or fabrication complexity. The antenna fundamentally relies on an aperture-coupled feeding mechanism. Energy seamlessly couples from the microstrip feed to the radiating patch through a precisely etched ground plane slot. The engineered air gap lowers the structural quality factor, exciting multiple closely spaced modes to widen impedance bandwidth and optimize VSWR. The antenna fundamentally relies on an aperture-coupled feeding mechanism. Energy seamlessly couples from the microstrip feed to the radiating patch through a precisely etched ground plane slot. The engineered air gap lowers the structural quality factor, exciting multiple closely spaced modes to widen impedance bandwidth and optimize VSWR. Broadband circular polarization is successfully achieved utilizing a sequentially rotated feeding network. This specific network distributes equivalent power to the four radiating elements while enforcing a progressive 90-degree phase shift between adjacent ports. Consequently, this mechanism expands the axial ratio bandwidth and ensures highly stable polarization characteristics. Experimental validation of the prototype demonstrates exceptional metrics. The measured return loss confirms a 62.9% impedance bandwidth, spanning 4.21 to 7.67 GHz. The axial ratio bandwidth covers 40%. The system delivers a peak gain of 11.5 dBi and maintains inter-element isolation exceeding 25 decibels across the band. Comprehensive diversity analysis verifies the array's effectiveness. The envelope correlation coefficient is suppressed below 0.0005, significantly below standard limits, ensuring highly uncorrelated radiation. As highlighted in the comparison table, this design offers superior bandwidth, peak gain, and isolation compared to prior works, while maintaining stable broadside radiation patterns. In conclusion, the strategic integration of aperture-coupled patches, an air gap, and sequential phase feeding produces an advanced antenna. By simultaneously realizing wideband circular polarization, suppressed coupling, and elevated gain, this proposed structure is exceptionally suited for high-throughput wireless communication within modern WLAN MIMO networks.